Good afternoon, everyone. Welcome to our session on Localizing Internet of Things, or IoT, for agriculture. And I'll be your moderator for this session. I am Leah Fernando Corpus from the Institute of Crop Science, CAPS UPLB. And we have our rapporteur, Mr. Brian Rolioque. And later on, I'll be introducing our discussants. Okay, so we will be hearing from Dr. Paolo Rommel Sanchez on his talk about cost-effective modular architecture for precision spraying using vision-based velocity estimation. But before he starts his talk, let me introduce our esteemed speaker. Okay, so Sir Paolo obtained his undergraduate degree in agricultural engineering from the University of the Philippines, Los Baños, in 2007. During the same year, take note, he ranked first in the Philippine Agricultural Engineering Licensure Examination. He later joined Del Monte Pacific Incorporated and worked for a year as a supervisor of 250-hectare pineapple plantations. He then went back to UPLB to obtain his master's degree in agricultural engineering. Since his graduation in 2011, he's been serving as a member of UPLB faculty and taught courses in computer applications, in engineering, and machine design. He recently obtained his PhD in mechanical engineering in 2023 under the Faculty Development Program of ERDT. Presently, he continues to serve as a member of the UPLB faculty in the Institute of Agricultural and Biosystems Engineering. His research focuses on machine vision applications for agricultural operations. He also worked on several Philippine government-funded projects, including the simulation of the hot water treatment of mangoes and the development of soil moisture sensor networks for irrigation scheduling. He also published and first authored several full-text papers on machine vision systems for agricultural applications. His recent works focused on low-cost modular designs for agricultural field robotics. Everyone, let's welcome Dr. Sanchez. Sir Paolo.
Thank you very much, ma'am, for the introduction. Okay, so today I'll be talking about cost-effective modular architecture for precision spraying using vision-based velocity estimation. It's quite a mouthful, but then I'll be talking about it in detail. So yeah. So one of the biggest problems in terms of the adoption of modern technology, digital technologies, robotic technologies, smart agricultural technologies is really the cost. And here in the Philippines, it's much more amplified given the value of our currency as well as the economy of the Philippines. So it's true in most places. So this is something that we would like to address. So our case, the case that I studied is in precision spraying. So precision spraying is essentially a conventional sprayer equipped with sensor technology. Typically, everything is moving now towards vision-based sensors. And then you have a control systems that triggers the sprayer if the target plant is detected. It also calculates the time that the nozzle would open or the solenoid valve would open. And then sometimes there is an optional velocity and location sensors. So this is implemented through GPS RTK or through wheel encoders. Now, why do we want that? Because we want to save our inputs. We want to make farming sustainable. So we want to deliver precise amount of inputs to our plants. Okay, so this is what have been researched or the status of the technology right now. So most of the researches are really leading towards fixed configuration, meaning you have one monolithic system. Okay, this is a problem in terms of, let's say, implementation in the farm, or has a limitation since different farms have different layout. Even moving from one vegetable, or even in the same vegetable, moving from one farm to another farm requires you to reconfigure your system. And fixed configured systems is limited, and it would take a while in order to reconfigure them. Then, as I've said, image-based sensing. So if you will look at literature's actual application, there are dedicated chapters for vision-based sensing because you could tell a lot coming from the images that being captured by the camera. And images are being processed nowadays using CNN. Before it was machine learning, SVM, histogram of gradient. Now the typical trend is to use convolutional neural network to perform object detection and localization. Okay. And then if you look at the studies, of course, in order to run your CNN model, it would require fast desktop CPUs. If you're into AI, you know that machine learning or neural nets, convolutional neural nets, takes a lot of computational power. Okay. And then typically, we have a non-offset layout. So this is advantage because you don't need additional sensors in order to implement the spraying. So the algorithm is simple. If you see a target drop, spray. However, this has limitation because CNN has a high computational power. That's why if you look at literatures, most of them are really operating at less than 1 kilometer per hour. This is to account for the processing time. Because if you have a long processing time, if you see process and then spray at, let's say, 1 second processing time, you'll no longer be targeting, or your target has already passed your nozzle, and then you will miss it. Okay, and then, so again, as I've said, fixed time delay, which is essentially the time you needed to process the image and perform and to actuate your solenoid valve. And then you have a fixed nozzle opening time, most of the designs. But nowadays, studies are moving towards variable opening time per nozzle. And then the number one technology in terms of localization and describing your motion of your equipment is through GPS RTK. Okay, and then in terms of cost, so this came from from one study that I cited. So 37.5%, or rather combined. So you see there the GPS plus GPS RTK is really cost a lot as compared with other sensors. Okay. So especially in the Philippines, as how I imagine this, let's say if we will implement precision spraying in the Philippines, you need to set up RTK base stations. And as I imagine it, it will be really troublesome. So just imagine the car industry is more luxurious industry, and then they would benefit more, or rather, they have more the finances in order to benefit to the RTK signal. How much more if we would implement it in agriculture? So so this research, we try to figure out what other technologies that we could use as a substitute to RTK, to GPS RTK. Because without RTK, your GPS signal is about 0.5 meters error. So again, the goal is to really simplify and innovate the design. We want to find alternative from GPS RTK. We want to make things reconfigurable. And we want to make things less expensive. So this is what we did. Instead of having a monolithic computing device, we divided each load into parallel low-cost computing modules. Because the idea is that if you have one expensive device that would break down, you have one expensive system to replace. And also, if you want to reconfigure, let's say a farm just requires one module. So it's easier to configure if you have modular systems. So that's the main idea. So each of the sprayer, the solenoid valve, the vision system, as well as the microcontroller, acts as a scalable unit, which you could install in different configuration. You can just have a single scalable unit or multiple scalable unit. You can mount this in a push type cart. You can mount this in a two-wheel tractor, or you can mount this in a tractor implement. So that's the idea. So single design for a lot of configurations. Okay, so first we want to test if it's really cost beneficial if we would replace an expensive computer with a low cost uh, board. So in this case, we have an RTX 2080 Super costing about $2,624 back then before pandemic and all of this inflation. And then we have a Jetson Nano costing just about $59. When we included all of the peripherals so that it would become a one-to-one ratio, it's about $228. So this is what we did. So first, we also look for suitable CNN model that will be able to run in this low-cost systems, embedded devices. So we settled in SSD MB1 and YOLO V5S. But during that time, I know right now Tensor RT is available for YOLO V5S. But back then, YOLO V5, Tensor RT was only available in SSD MB1. And if you look at that chart, if we apply Tensor RT, which is built in Jetson Nano, to SSD MB1, you could see a significant rise in the, in the frame rate per dollar that the Jetson Nano could process. So we settled on using SSD MB1, optimized in Tensor RT, and then running on a Jetson Nano. Okay. So next thing that we wanted to do is to eliminate the GPS RTK and to further simplify the system. So first is modularity. Second is your camera is there. The idea is that people usually has the capacity or have the capacity to track objects, okay, and predict them. And that's what we want to implement. Well, the device already has a vision system. Why not use it to track objects and predict when to spray? So what we did is we calibrated our camera to track the motion of the bounding box generated by the neural net between consecutive frames. And using the motion of that, we just applied a factor in order to convert the pixel per second into the actual distance of meter per second. Okay. So, but then again, it's not realistic to really, if you are going to use the system and you're going to the field, that you will need to calibrate everything. So we think of an analytical way in order to convert the pixel per second into meter per second. And then this is what we did. So essentially before, what we thought was the bounding box was at the ground, but we're getting a lot of errors. So what we did is we applied a plant height factor. And then based on our tests, it's just in between or just half the plant height based on our test. We tried to change the plant height factor, and then it came up the part in which it has the least error is actually when your plant height is around 0.5. So this gives us a better idea. So the analytical solution that we derive just means that I just need to sample some plants and then measure their height. And then just half of that height, that's where the bounding box is. And based from our tests, so we have this error. So it's about 3.4 or 3.4 or rather, yeah, 0.034 meter per second error. If you multiply that with the frame rate, it's just about 2 millimeter error in actual distance. Second, we want to make it faster. So what we did, instead of having a non-offset layout, we offset the nozzle away from the camera. This would allow us, okay, to have a delay in terms of detecting and spraying. Because the travel time would allow us, or give us this leniency. So what we did, we also put the velocity estimation region at the center so that we would prevent significant optical distortion. Okay. Okay, so this is what we did. We first did a simulated outdoor experiment, and based from our result, we have a high accuracy and precision. Okay, we recorded just about 3% incorrect spray, and 100% all of our targets were sprayed. And we were able to do it at 0.87 meter per second, or about 3.1 kilometer per hour. To give us some context, typical spraying is done at around 3 to 6 kilometer per hour. 6 kilometer per hour if you're using a tractor. And then if it's a push type, essentially it's about a kilometer per hour. Okay. So next idea is to test it in the worst possible scenario, which is a broadcast seeded soybean. And this will really is the worst case scenario because you don't have uniform arrangement of plants. You're not distributed in terms of hills, regular spacing. So we trained our machine learning model for the soybean. So this is a sample of that. We get about a mean average precision of 76%. And then we tested it in the field. The soybean field has a lot of weed population. Much of the detail is in the paper that we publish on the distribution of the weeds across the field. But overall, we sampled, and then 60% or 67% of our target or non-target plants has adjacent weed. So meaning, because of the broad or the effective nozzle area of our sprayer, so most likely it will be sprayed. And we observed just about, instead of 67%, we observed 74%. So we observe about 7% increase in the error. Okay. But in terms of variable rating spraying, on maximum we reduced the amount of spray by 49%. Of course, in the area or in the row that has the least amount of weeds, that's where the maximum reduction is. And then the area where most of the weeds are, or the row, that's where the least amount of reduction was observed, which follows our prediction. Okay, so key takeaways. So first, it is possible to minimize the impacts of spray operations, of course, using precision spraying and low-cost technology. And then number two is that it's already proven that CNN works. The challenge is to make them useful in real-time application. So instead of, let's say we have a two-stage spraying operation, first is mapping, processing, and then finally you do the spraying. So we want to make it real-time so that the lag time between image capture, map processing, and then spraying will be eliminated. Okay, and then we can grow the technology. All of these equipment, all of these technologies are available in the Philippines. And as I mentioned in my previous, in the discussion, previously, the real challenge in government institution is really the procurement of these equipment. Because as I checked, there are local suppliers, but most of these are really available abroad. But there are local suppliers. Okay. I guess, and then all of the technologies that we've used are open source, except for one. Because we still depend on CUDA, which is a proprietary technology. So I guess that's it. Thank you very much.
Thank you so much, Dr. Sanchez, for giving us a glimpse of your work incorporating IoT in agriculture. So now let's proceed to the discussion part. Let me first introduce our two STEAM discussants. So first we have Professor Russell McMahon. So he's a professor emeritus at the University of Cincinnati. He has been teaching IT-related courses since 1980 and has been a faculty member in the School of Information Technology since 1999. In 2014, he spent 6 months working at 3 universities in 3 different countries. That's Rwanda, Kenya, and South Africa. Okay, so he helped develop an IT. He helped develop IT curriculum and has been giving talks on creative problem solving. And in the past 2 years, he has given workshops on improvisation for scientists and technologists to enhance their communication and teamwork skills. He is also a US Peace Corps response volunteer currently deployed to UPLB. So thank you, Professor Russell, for sharing your time with us this afternoon for the talk of Dr. Sanchez. And also we have Engineer John Paolo A. Ramoso as another discussant. He's an assistant professor at the Department of Electrical Engineering at UPLB CEAT. He obtained his undergraduate and master's degree in electrical engineering at UP Los Baños and UP Diliman, respectively. He's planning to take his PhD degree in biomedical engineering, focusing on diagnostic services. Should I say the university? At Brunei University. So Assistant Professor Ramoso is part of the project ATOT, Aided Farm Management, for the optimized production of selected high-value crops, and is currently leading the project development of a CNN and RNN topology for impedance spectroscopy analysis. Okay, so may I invite our team discussants and speaker in front? Professor Russell, your microphone. This from here. Okay, so let's have this time for our discussants to give their views related to Doc Paulo's talk. Maybe we can start with Professor Russell.
Okay, thank you very much. And it's a pleasure and an honor to be here. Truly, truly is a great institution here and the university as well. So, and I'm going to get to meet some really, really neat people here. I know that already. So the talk was very interesting, and I just sort of put down timelines when you said things. And so I'll give you a few things. First off, you started out with the most important part. It's cost savings. And it's interesting you said it because at lunch, it's exactly what I was talking about with the person I had lunch with today. It was just on cost savings. Because if it's not beneficial to the farmer, why is the farmer going to use it? Other than it's cool technology, it really is. But why are they going to use it? So cost savings comes down to an extremely important component there. Otherwise, it's just going to sit in a garage somewhere and it's going to rot away eventually. And it'll be an interesting toy children can play with, but that's all. So that's an extremely important component there. And then you went through the various components of how effective it was. You really I felt you showed it pretty well demonstrated. Obviously, you've got to begin to think, what do I scale up? What other types of plants? Where can it be used? What are the limitations? Because you always find a limitation somewhere. There's some part where it's just not going to work. And that's fine. That's what you want to find. And it's more important that you find where you fail because somebody else later also can succeed maybe. So that was important. Another interesting aspect, since I do teach data visualization, be careful of colors. And that very first one was the kind of sort of a pie chart. And first off, I'm red-green colorblind. And it's really hard also to see where the axes are, which color matches up to which thing. Just make a simple little table with a little bar chart there. A lot easier to read and see and relate to, at least for people like me, for sure. So even you said keep it simple, keep that simple as well. So that's kind of an important part there. I love the fact they're using open source. That is so key today. And open source has shown that it can be used. There's one interesting aspect you need to look at, though, and that is in cybersecurity area. And that's another area of things that I've spent time studying. IoT, of course, a few years ago, all the many of the IoT devices were put into a botnet, and then they were doing denial of services against some really big companies in America that then crashed. So security is another consideration you really have to look at. Even open source has security problems. And so, yeah, it's free and can be used, but use at your own risk. And not all open source projects continue. So what happens if suddenly this open source project dies? What's the alternative? What backup do you have available? These are things that maybe you don't necessarily have to look at, but somebody along the line when you form a team is going to have to consider some of those areas. As I said, overall, this was an excellent presentation. I enjoyed it, learned a lot, got to see some. I spent time beforehand reading the previous paper and other previous papers other people have written. And so I've learned a lot about just the data visualization aspect in terms of being able to recognize an object and using Microsoft Cocoa and some of the other libraries that people use to build the image knowledge within the system. So yeah, it was fun. Yeah.
Thank you, Professor Russell. Maybe we can request some response from Sir Paolo.
So thank you very much, Professor, for those key points. So going back, our main library that we're using is actually robot operating system. It saved me a lot of time because before we thought we need to develop all of this framework, but then we realized, oh, there's robot operating system that we can make modular robotics, implement them. They're already drivers, all of these things. So yeah, if you're interested, you could start taking a look at the robot operating system. It's now in version 2 to improve the security. So one thing that, yeah, as you can see in the problem or in the among the final slides, is the low precision of the system in terms of, let's say, spraying when you have adjacent weeds right next to the crop. So right now, what we're working on is instead of just one nozzle, we're working on an algorithm to have micro nozzles. So this would allow us to spray only a smaller region and then probably, hopefully solve that problem. We're confident. And then in terms of security, we're also moving towards edge computing, having an edge server instead of just a cloud server. This would also improve the latency. Instead of like sending the image or a processed data into the cloud, it would be much faster if you will have an edge server.
Okay, thank you so much. I'm learning a lot from here because I'm from another discipline. I'm a chemist. Okay, so let's hear from Engineer JP.
Congratulations, Dr. Paolo, for the presentation. It was very thorough in terms of you have shown the raw data, that's the feed actually from the camera. So at least we can see that it can track real time as it was flowing through the field. I think 1 kilometer per hour. That's the running rate, right? Actually, I have two questions. First is, one will be about the cost effectiveness part of the robot, and then the second one will be about the value chain of the electronic components. So the first question would be in the cost effective part. Did you try to monitor the power consumption of the processing power of the Jetson? I think you used Jetson Nano, right? So during the field trials, were you able to use how much power? How many runs was you able to? I believe you used power banks maybe to run the Jetson. Yeah. So I have read some papers that they are looking into the power consumptions of deployable sensors and deployable servers, so that it would be integrated to the cost efficiency of the of the hardware itself. I'm quite interested in that part because I'm also deploying sensors, and then one of the main factors will be how many times should I charge it during one cropping season. So I don't know. I'm just interested in the data. Do you have any uh, measure data on that? Thank you.
Okay, in terms of the power, I just monitored it in the laboratory. For the peak power consumption, it stays there at 15 watts. And then we have a more detailed study. We will publish this within the year. In terms of what we did is we chopped the CNN and try to see what we the cost effective architecture. If some of it will be processed in the edge device, then some of it will be processed in the edge server or in the cloud. So we have a study on this. We presented the paper in IEEE last month. So hopefully the full paper would come out this year. So on the detailed power consumption. So
I'll
yeah.
be waiting for that.
Yeah,
It's very
definitely.
interesting because I'm coming from an electrical engineering standpoint,
Mhm.
and one of the key questions we're always being asked when we're deploying sensors or robots, how how long and how much time should I charge this? How many times every cropping season? Yeah, those questions. And building on the comments of Professor Russell, um, I think one of the uh, uh, key factors that would elevate the usefulness and the cost effectiveness of the robot is how much savings will the farmer create from, for example, in this weed sprayer. So have you? I think the end goal there should be how much savings did the farmer was able to generate from using that device.
Yeah.
So yeah, I think it's a good direction on the on robot deploying a robot in the real field. And the second question I was supposed to ask is more on the because I am used to instructing my students to create sensors and their own deployable whatnots. And one of the feedback, most of the time, the feedback we are getting from our students is here in the Philippines, and most of I believe most of the third world countries, is that it would take time before sensors that were developed, especially in Europe and US, before it reached here in the Philippines. So, for example, Raspberry Pi 5 was already launched earlier this year, but until now it hasn't reached us here. So, yeah, um, do you have any comments regarding how can we push on generating this cool text or this because I believe Asians and well, here in the Philippines we have great minds that create systems and these cool gadgets, but we are constricted in the value chain before I mean when will the device get here? Yeah, so very restricted in technology wise, and I think I don't know. In your experience, have you experienced this kind of phenomena wherein we can see in the internet, ooh, we could use this, and then
relate.
yeah, before we could use it here, it would take usually 1 year before we can get cool stuff and sensors. Yeah.
Okay. First off, to answer the first question, in terms of cost effectiveness, we were not able to do the economic analysis, but the reality in terms of precision agriculture, precision spraying, there's a sweet spot. You need to capitalize on the economy of scale because the cost of the equipment should be justified by the amount of savings in the herbicide or fertilizer of the farmer. So there have been countless studies on this that yeah, there's a sweet spot. But for our machine, right now we haven't done, to be honest, we haven't really done that. But of course, the plan is to really go to do that. And the advantage of the system that we're proposing is that this is scalable. Depending on the size of the farm, we could just implement a single scalable unit or two scalable unit. Unlike if you're stuck with fixed modular system, you have a big expensive device and you want to maximize the use of that. So that's for the first question. Now for the second question, yes, I experienced that. And that's where modularity comes in. So my idea is that we could develop some functionality in one module while waiting for the PCB or the board to arrive. And then once it arrived, we could now develop the technology that will utilize that particular equipment. So that's why I'm an advocate of modular designs because it simplifies, although there are weaknesses in terms of modularity, but I believe in agriculture. Agriculture has been always a user of modularity. We have a prime mover, a tractor, and then we have implements that we could really replace depending on the operation. So in terms of agriculture, I believe modularity is one of the technologies that we should further utilize, especially in robotic designs.
Thank you.
So I have one question to ask you. Did you try to measure mean time between failure on any components just to see how long it can really, last? I mean, because that always happens, and you need to know just because you eventually want to improve upon it. It's not that you have to worry about it at this point, but before you ever go to commercialization, you have to, yeah.
Thank you very much for that question. It's actually, aside from cost, the other reason why there's low adoption in terms of digital technology, smart agriculture, robotic systems, is the fear really of the reliability of the components and equipment. And then, to be honest, we haven't tested that, but up to now, it's still working. So it's been 2 years, 3 years, it's still working. And even the components that we're using and then allowing the students to use, it's being mishandled a lot of times by our students. So far, they're still surviving. So, yeah.
If I may add, one curious thinker I've been thinking is that I believe you deployed this in the US, right?
Yeah.
How would it fare against maybe weather from the tropics here? Would it be still robust enough to last the 2 years? 2 years of working field robot is actually quite impressive. So I was just thinking how would it fare against tropics or I don't know other weathers.
So I think the challenge right now, we didn't test it for humidity because we tested it really under the sun at about 96 Fahrenheit or about 30 plus degrees Celsius, 37. So it's really hot. And then it survived. But in terms of the humidity, because it's between like making it IP, giving it using an IP rated case, but at the same time you have to be creative in terms of the heat management and ventilation of these PCB. So our direction right now is really using more simplified components, and if possible towards edge computing.
All right, thank you. Okay, so maybe before we end, let's open the floor for questions from our participants. Anyone? Pose questions? Or maybe you may want to collaborate with the team of Dr. Sanchez. This can be a point for or a time for collaboration. Yes, sir. Please introduce yourself and affiliate.
Arnel po, ASI. Sir, does this change the amount of active ingredient per hectare, the recommendation, because those were standardized from mass spraying? Are there studies about this?
Actually, that's also one of my questions when I was doing the study, because the recommendation is in terms of, let's say, gram per hectare, liter per hectare. So now that we're doing precision agriculture, it will really change the efficacy, or I mean the true. To answer the question, I'll be honest. It's still like a question in my mind, but I can cite other studies, and then this is one of the tests that I did, is to really just measure the accuracy of the system in terms of does it really hit the target. There's another test which is you will utilize actual herbicide. We were not allowed by the farmer to use actual herbicide, but then this is one of the tests, and then you have to, let's say, count the weed population before and after. So using the same, let's say, dosage recommendation, let's say you have this travel speed, etc. But and then their result was there's no significant difference between uniform spraying and precision spraying. But then again, I think a more thorough study is needed in terms of the efficacy. Yeah.
So in short, we have to
Mhm.
revisit the science of standardizing the dosage in precision agri.
Yes, even the test. When you that's the hard part also in terms of the review of literature. There are no standardized tests for precision spraying. Some are, let's say, they have a hill spacing of 1 meter. Some have precision spraying or hill spacing of 30 centimeter. My test, I did that at 30 centimeter. So if I did that at 1 meter per second, I don't have wrong spray, or rather 1 meter hill spacing, I don't have wrong spray. So those are the things that are needed to be standardized so that when we compare results, it's a lot easier.
Okay, thank you. Any other question? Okay, yes, Sir Brian. Anyone from the industry here? Maybe we can hear from them about their thoughts about the technology.
Good afternoon, sir. I'm Brian from Erie. So I just want to ask, currently you're using this for herbicide applications, right? So as someone from the crop protection niche, I just want to ask if you are planning to extend this to, say, crop pests like insects and pathogens like fungi. And also, I'm just curious if this technology will be available to our farmers. How much do you think will it cost them?
Okay. So going back to the question, again, this is a modular system. You can simply use the vision module, or you can use the spraying module. So again, yeah, we could use it, and then you could simply change the CNN model. Right now, you can train a CNN model for weed detection for this type of crop, for this type of weed, and also we could test or train another CNN model just for identification of pests and yeah, insects. And then go on the second question, what are again, was it the future direction? What was the second question again? Thank you. Sorry.
My second question is, if this technology will be available to farmers, so how much do you think will it cost them?
Okay, so I'll give you the breakdown of the cost. Yeah, the board right now is just around 8,000 pesos. Camera, it depends on which one you want to use. It's you can use 1,000 pesos RGB cameras, equip them, etc. It's essentially a scalable module, can be less than 30,000 pesos. It's still expensive, but yeah, compared, if you look at the table that I presented, it's a lot cheaper compared to what we have right now. So yeah. So when right now, I'll be honest, because this has been asked along like 6 months ago. Like, are you planning to start up a company? Well, I love to, but it's really the amount of time that requires to start up a company or to license these technologies. So it's really probably some students of mine would pick up this idea and then start up a company for this. So again, so I've been talking with TTBDO regarding technology licenses, all of these things, and even considering open source. So yes.
Okay. Yeah, I agree with you, sir, because we were required in one of our projects to start a company. And when we talk with investors, so we have a spin-off, the investors require you, or they prefer full-time partners. Maybe you have when you retire,
Yeah.
or you can have a partner industry. When you can have a partner industry.
So it's something that we believe in. The Filipino culture is still not, in terms of innovation and then go transitioning into the commercial space. It's still a developing, I think, area in the Philippines. And I believe in the academe policies regarding this, or giving actual time to the faculty members to start up. and all of these things.
Yeah. Oh, any other question? We can entertain one more. Anyone? Yes, sir? Sir Ardell.
Sir, I apologize because this is not my field, so I am not familiar.
Questions are very much
Are the parts, can they be locally fabricated or locally sourced? Because if we want to introduce it to farmer, if we import the parts, then the prices will be volatile.
Yes, actually, they are. I have one student working under me under the ERDT program. She already had her LIB, her line item budget, and also references of where she got all of the prices, and all of them are local. So yeah, the answer is yes. And hopefully we could have, because what I'm doing right now, since all of the administrative jobs and research and then teaching, all of this stuff that's going on, what I'm doing is really mentoring all of my graduate students and to continue working on this project.
Okay, thank you. Okay, so at this point, anyone from the ICT here? Do we have the certificates? Maybe I'll request Sir Brian to assist us for the certificates to our discussants and our speaker. Okay, so let me first present this token, our certificate of appreciation, to Assistant Professor Paolo Rommel Sanchez for his talk on cost-effective modular architecture for precision spraying using vision-based velocity estimation, given this May 29, 2024 at the Erie headquarters, Los Baños, Laguna. Signed, Mr. Benedict Hardinero and Miss Janelle Joseph. Okay, thank you, sir. You can see here. Then for our discussants, we first award the certificate to Professor Russell McMahon as discussant in the breakout session of Dr. Sanchez, given this May 29, 2024 at the Erie headquarters, Los Baños, Laguna. Sir, we can have our photo opportunity. After we award the certificate for Assistant Prof. Jan Paolo A. Ramoso for being our discussant in the breakout session for cost-effective modular architecture for precision spraying using vision-based velocity estimation, given this May 29, 2024 at the Erie headquarters, Los Baños, Laguna. Okay, thank you so much, sir. You can stay here, our resource speaker.
Thank
Yeah.
you.